Hello all. Welcome to uh, Let's Talk Astronomy session. My name is Supriya. Uh, a very warm welcome again on behalf of our team. Uh, as you know, this is a online interactive session as we try to adapt to the new normal way of living by staying at home. uh, uh, we should not stop ourselves from learning something new. So, keeping this in mind, a few of us came together to organize these sessions uh, to see if we can tell you more about the challenges and the research that is currently involved in the field of astronomy and astrophysics. So we are people scattered in different parts of the world, and all of us are involved in the research of astronomy and astrophysics. This is our team. Like I said, we all are at different parts of the world, and this is an outreach program for all of you guys. It's not a certificate course. We are not associated with any organization. So, in this session, we plan to give a broad overview of astronomy and discuss the challenges involved. By the end of the session, we will also discuss different possible career options if you are interested to pursue astronomy further. So, we strongly encourage you to make your most of this time, that this another 2 hours of these sessions, and get actively involved in the question answer session. So, the session is broadly divided into two sessions. The first session will be about the daytime, that is the sun that we see in during the daytime, where we present some of the unsolved problems and the facts about the sun and like the observational challenges that is involved. And in the next session, we'll talk about the night sky and about the planets, the stars, and the cosmology, and the instrumentation part about how the telescopes are built and what are they, and uh, again some unsolved challenges in each of this field. So this is how the session is divided. Each of the session is for broadly for about 20 to 25 minutes. And after each session, we will have a 10-minute question answers where you can send us your questions. I'll tell you how, and we will try and answer them. So, like I said, the first session will be about the daytime astronomy and a question answer session. Next, about the nighttime astronomy, and again a question answer session for 10 minutes, and the career option session. And we have a longer question answer session there. So for you to send us the question, you will see the link below your in the YouTube description below the YouTube video. You can click on the link and you will see this page. Or otherwise, you are familiar with our web page, you can go to our web page, and here you will also see the option to click here to ask a question. And if you click there, it will again take you to this link. Through this page, you can send us the questions wherein you type your name, email ID, and for each of the sessions, we have different categories. And in you can type your daytime session in the first category here, and during the nighttime here, and the career session in the third category. We will really appreciate any comments and feedback that you have. And okay, remember, once you type your question, click the submit button, and we will have your question. And in the question answer session, we will try and answer them. Okay, and again, I emphasize, try and ask as many questions as you want to, and whatever questions you have regarding the slides that we show, or any other general question related to astronomy and astrophysics that you have. And these are the general instructions I already spoke to you about. And the presentations that you see from now on uh, will have a slide number If you have any specific question to any particular slide, you can also note down that number and type in the number and your question. So let's start with the first session, and I invite Avijit now to take over and present our first session that's about daytime astronomy, which will be about our sun.
Thank you, Supriya, and welcome everyone to this first session. As I think my video is off. Just a moment. Great. So welcome everyone to the first session. As Supriya mentioned, this session is all about daytime astronomy. So when we asked you all to fill the form and ask us any question, then most of you asked us about the galaxies, the black holes, and many more fascinating things that we see in the night sky. But not so many questions were asked about the sun. So we thought that we'll inform you in an individual session about our nearest star, the sun. So as you already mentioned, that each of the slides has a slide number at the bottom right corner. So if you have any specific questions regarding any slide, then please note down the slide number and type in your questions in the chat window. So let us start knowing our sun in a better way. So we live in the solar neighborhood, and its existence influences our lives, starting from the food we eat, and it also provides us energy, which brings us life to our planet. It defines our seasons from summer, spring, autumn, and summer. It also has its timing to our heartbeats, and it also influences the sleep patterns for all the living creatures on Earth. Now, there are billions of stars in the Milky Way galaxy, and the sun you see here is just one of them. But it is also our closest star to the Earth at a distance of 150 million kilometers. So, understanding the sun will help us understand all the stars in the universe. Now, our sun is very dynamic, as you can see here, and it changes constantly. So, could it be dangerous also? And can we do anything about it? Now, let us try to understand in this talk why our sun is so dynamic and what effect it could have on all of us. So to do that, let us start by looking at the structure of the sun. Now, the sun has multiple layers, like an onion, and each layer is different from other and plays an important part in producing or transferring the light that we receive on Earth. So let us start discussing each of these layers. So let us start with the centermost part of the sun, which is called the core. Now the core is approximately 15 million kelvins, which is the hottest part of the sun. Now, how hot is that? To get some idea of these numbers, let us look at something which is more familiar to all of us. The average human body temperature is about 310 degree Kelvin or 37 degrees Celsius. And the molten lava, which comes out during a volcanic eruption, has a temperature of 1000 to 1500 Kelvin. Now, compare it with the temperature of the core of the sun, and you can imagine how hot it looks. So from now on, pay attention to the temperature of each of these layers that I mentioned, and I'm sure that you'll be surprised later on. So now let us look deep inside the sun. Now there's a three-step process that takes 4 hydrogen nuclei and fuses them together into a single helium nucleus. Now this helium nucleus is slightly less massive than the 4 hydrogen nuclei that combine to form it. And then the extra mass is converted into the energy. And this produces, this energy is converted in the form of gamma ray photon. Now, these gamma ray photons travel to the next layer of the sun, which is the radiation zone. Now, the process of energy transport is radiation, and hence the name. This is similar to the case when you're sitting in front of a fire to warm your hands, and the heat reaches you through radiation. In this layer, the temperature drops from 15 billion Kelvin to 2 million Kelvin. So as we are going out, we see that the temperature is sort of falling down. Now let us come to the next layer, which is the convection zone. So you see this is the base of the convection zone, and this is the uppermost layer. Now the convection zone is the outermost layer of the solar interior. Now the transport of energy from the edge of the radiative zone to the surface happens through giant convection cells. It is similar to a pot of boiling water, and the plasma at the bottom of the convective zone is extremely hot. It bubbles up, and as it reaches the surface, it loses heat to space. And once the plasma bubble cools, it sinks back to the bottom of the convective zone. But we cannot see any of these layers which are happening in the interior of the sun because the sun is opaque. Now, the boundary past which we cannot see is called the photosphere. So the photosphere is termed as the surface layer of the sun. The term photos derives from Greek word meaning light. And even though you can see that the sun looks very sharp from it, only from a distance, if you take a closer look through a telescope, you'll see that it is made up of giant cells. You can see this granulation pattern over here, and each of this granulation is typically about 700 to 1,000 kilometers in diameter. And so this particular image was taken from a telescope called the Daniel K. Inouye Solar Telescope. And this is the largest solar telescope that we have currently. So the visible surface of the sun is at a temperature of 5,700 degree Kelvin. So you can see that we started with the core of the sun, which was at 15 million Kelvin. And now we have come to the surface, which is at 5,700 degree Kelvin. So now when you zoom in and when you look at the movie of the surface, you can see that the convective bubbles that we were talking about. So each of these cells is a convective bubble. The bubble is rising from the bottom, cooling down, and then falling back again. Now there are two more layers above the photosphere. One is called the chromosphere and other is the corona. But why don't we see any of these layers above the photosphere? Think it like that. Imagine a candle that is kept in front of a light bulb. Now, do you see the light coming from the candle? No, right? In the same way, the photosphere is so bright that we do not get to see the relatively faint light coming from the chromosphere and corona. However, during a total solar eclipse, when the moon masks the photosphere, we can see the light from the chromosphere and the corona. You can see here. So the moon is blocking the solar disk, and now we are able to see the faint radiation that is coming from the chromosphere and the corona. Okay, so now let us look at the structure of this chromosphere. So now the chromosphere is above the visible photosphere, and it is at a temperature between 4,000 to 8,000 degree Kelvin. So you can already see something funny is happening. Now, instead of the temperature dropping, we're seeing a slight increase in the temperature. Now, what happens when you go to corona? The corona extends beyond the interplanetary region, and it is at a temperature of between 1 to 20 million Kelvin. So you must be wondering, how did it become so hot now? And we'll come to that. But before that, let us look at the image of this beautiful image of the corona that was taken during the recent solar eclipse in 2017. You can see that to the extent how long this corona exists. And it is because of these patterns, these crown-like patterns, the word corona comes. Further, did you also notice that there are so many other structures on the sun? Like there is this dark sunspots on the photospheres. Okay. And then there are these bright regions over here, which are called flares. And then there is something hanging over here, and this is called a prominence. So what are these structures? And like coming back to the temperature again. So we have the photospheric temperature 5,700 Kelvin. The temperature slightly increased to 8,000. And then we went to corona, it became 20 million. So what is heating the corona to such high temperatures? So and this is a very big puzzle, and we still don't understand what is the answer to that. So it would be something like that. Like imagine that you have these two men sitting in front of fire and they start to move away. Will they continue to get the same heat? No, right? We will think that as they move away from the source, as they move away from the fire, the temperature decreases. In the same way, as we move away from the core of the sun, where the energy was being generated, the temperature should have decreased. But now we see that it is increasing. So what is happening? To understand that, we have to see what is the sun is actually made up of. Okay, so what's happening in the sun? The sun is actually a huge ball of ionized plasma. It has ions and it has electrons in it. And these particles that in turn carry a magnetic field, which makes the sun a huge magnet. Now, how strong a magnet is the sun? To compare, you all know that the Earth also has a magnetic field because of the motion of the iron core. And the strength of this field is about 0.5 gauss. Also, if you take a bar magnet that you see every day in your lab, it will have a magnetic field around 100 gauss. But however, the magnetic field in a sunspot, it is around 1,000 to 4,000 degree. So now these magnetic fields, which are present all over the sun, because the sun is a giant ball of plasma and it also rotates, as the sun rotates, it carries or it drags the magnetic fields along with itself. And the sun does not rotate as a solid body. The sun, in the equator of the sun, rotates faster than the poles. So as it is spinning, it drags the magnetic field along itself. And because of this dragging, the magnetic field sort of makes these loops, knots, and kink-like structures. So what happens is that these knots or the loops of magnetic field concentration, they sometimes become buoyant and they rise up above the surface and they form these strong magnetic field regions called the sunspots. And the magnetic field in the sunspot is so strong that it does not allow any heating to happen from the layers below. This makes them much more cooler than their surroundings, and hence they appear dark. How big are the sunspots? The sunspots can be, see here, the sunspots can be as big as the Earth, or sometimes much bigger. They can be as big as the planet Jupiter itself. Further, the number of sunspots changes over a cycle of time. So the sun has an 11-year cycle. So there are times called the solar minima, when there are no sunspots on the sun. And then there's a time called solar maxima, when there are a large number of sunspots. Now, the magnetic field is not only restricted to the photosphere when you see sunspot, they further extend to the next layer also. So when you look at the chromosphere, and this is the image, they appear as this dark filaments on the disk. And when you look at them from sideways, they appear as these prominences. So these structures that you see in these dark structures called filament and these structures called prominences and the sunspot that you see on the photosphere, they're all manifestations of the same magnetic field loops when seen at a different layer, at a different temperature, at a different orientation. Now, what happens is that sometimes these magnetic field lines, they are stretched into the corona and where it can break. It's like if you keep stretching a rubber band, then it breaks after a point, right? In the same way, when this breaking happens, when the magnetic field breaks, the energy is released, resulting in flare and a coronal mass ejection. So a coronal mass ejection is a huge ball of plasma that has been ejected in the interplanetary space. And how strong is this explosion? You can see this this is the flare, and then this prominence is erupting, and the huge ball of plasma is sort of ejected into space, and sometimes it can reach even the Earth. So how strong is this coronal mass ejection? It is as huge as exploding millions of hydrogen bombs that we saw that were dropped in Japan during the Second World War. Now, all this energy is carried along in terms of ionized particles that are released in this interplanetary region. Now, this CME is usually emitted in all the directions. But if it is emitted towards the Earth, then we should be concerned, right? So what happens when this huge coronal mass ejection reaches towards the Earth? What happens is that we see them, when they reach these ionized particles, they they interact with Earth's magnetic field. And you can see that they sort of follow the Earth's magnetic field, and then they hit our north and south polar regions. And when they interact with Earth's magnetic field, they produce this beautiful brightnings called the aurorae. So you all must have seen images of aurorae, which are this beautiful green or lightning in the upper atmosphere that occurs near the polar region. So whenever you see these beautiful images, imagine that or remember that this is happening because there was a huge explosion on the surface of the sun that was like exploding 100 million hydrogen bombs. So apart from the beautiful aspect of seeing aurorae, what are the harmful aspects of the coronal mass ejections? They really impact our space weather. So, and this impact could be like disrupting of our communication devices. So your TV may not work, your cell phones may be down, a high-speed train may lose, or if there is an astronaut in space, he or she could be put in great danger. So this is one of the reasons why we should study and understand the sun so that we can predict these events and protect ourselves from it. So how do we study the sun? So before we see how to study, the first caution is that you should never look directly at the sun through your naked eye. It will damage your eyes. So we should always use a filter. And the way we actually study is not through looking at the sun, but something called a multi-wavelength observations. So what are these multi-wavelength observations? For example, the human body looks different at different wavelengths, right? So you have this electromagnetic spectrum. So what we see usually is the visible light, which is only a small part of that. But you have beyond the visible light, you have the infrared, you have the longer wavelengths called the radio waves. And in the shorter wavelengths, you have the ultraviolet and the X-ray. And you all have heard of X-ray because when we break our bone, we go to the doctor and he asks us to take an X-ray. And this is how a human body would look in an X-ray, right? We all know how we look in a visible light. This is what we see. You see the skin and you see the face. And in an infrared, we get to see like how the heat is distributed in the body. So you can see these bottles, they appear darker because they're colder. And then the rest is the human body temperature. So you see that the same human looks different at different wavelengths. So in X-rays, in visible and infrared. In the same way, when we want to study the structure of the sun, we take images of the sun and different wavelengths, and we see different structures. Now, to do this, the technique that we use is called spectroscopy. Okay, this is what happens when you get a rainbow. So, for example, when you pass a light through a prism, the white light is broken into its constituent wavelength. So you see all this from colors from red to blue, similar to a rainbow. And over here, you see what happens when you pass sunlight through prism. This is called the spectra of the sun. Now, the sun emits electromagnetic radiation in all wavelengths, starting from X-rays to radio waves. But because of the Earth's atmosphere, it blocks some of the wavelengths, and only visible and the radio wavelengths can reach the Earth. And all other wavelengths like the gamma rays, the X-rays, the ultraviolets are blocked by the Earth's atmosphere. So if you want to study the, the sun in these wavelengths, which are blocked by the Earth, the gamma rays, the X-rays, the ultraviolet, we have to go in space. So that's why we have these satellites that observed the sun from space, as well as we have some of the observatories that observe the sun from the ground. Okay, so this is how the Earth sun looks when we are observing in ultraviolet channels from the space. So these images were taken by the Solar Dynamics Observatory, and there are many more telescopes and observatories that have been observing the sun from the ground as well as from the space. So you have this solar orbiter that was recently launched from the European Space Agency. We have this Daniel K. Inouye Solar Telescope, which is in Hawaii. It's the largest telescope on ground from the National Solar Observatory. And recently, NASA launched the Parker Solar Probe, which goes very close to the sun, almost reaching into the solar atmosphere and observing the particles. So, what are the observational facilities in India that observe the sun? So, we have the Udaipur Solar Observatory in Rajasthan. So, you see this dome, and this is where we have the telescope sitting in the middle of a lake. We have this Gaudividin Radio Observatory in Karnataka. And in Tamil Nadu, we have the Kodaikanal Solar Observatory, which is one of the oldest solar observatories in India and the world as well. And the Kodaikanal Solar Observatory has various telescopes like the H alpha telescope, the WARM telescope, and these instruments. And it has been collecting data for like from 1904 onwards. And if you want to look at this data and how the sun looks over the years, over a 100-year cycle, you have images in white light and other wavelengths. And if you go to this website of the Indian Institute of Astrophysics, then even you can access the data and play around with that. So this is about the ground-based facilities for observing the sun. What about space-based? India is now planning to launch Aditya L1 mission, which will be the first solar mission having 7 periods observing the sun in different wavelengths. Now, this satellite would be placed at the Lagrangian point, which is a point where the gravity goes to zero. It's a stable point between the Earth and Sun's orbit. And this is expected to be launched around 2021. So keep an eye for that. And if you also want to be part of this facility and explore the sun in more detail, then wait for our session on career guidance, and where we will be telling you how you can join astronomy institutes. And if you have any more questions, please send them to the Q&A link that we have sent you in your email and even in the YouTube description. So now the time will be open for questions. Thank you.
Hello, can you hear me?
Yes.
Thanks, Abhijit, for an excellent talk. Yeah, so now we have some time for questions. So before we start the session, I would say please keep sending in your questions. We have a couple of interesting questions, but please keep sending in if you have more questions, while some of the questions already sent being answered. So we have our first question from Nakul. So this question is for Supriya, and the question is, what is the temperature of sunspot? Supriya, over to you.
Yes, hi. Like before moving on to what exactly is the temperature of the sunspot, what you should keep in mind is that we see them dark because they are much cooler than the temperature of the photosphere that you see. Like Avijit showed you in the slides, wherein the temperature of the photosphere is now around 5700 Kelvin, but the sunspots are usually of the temperature 3000 to 4500 Kelvin. So because of this difference in the temperature, you see them dark. And why? Like he explained in the talk, it's because the magnetic fields are so strong in these regions that they don't allow the heating that is happening with at different layers from the lower layers to come up. So they're cooler than the surroundings, which is around 5,700 Kelvin. That's the photosphere, like I said. And these sunspots are usually around 3,000 to 4,500 Kelvin. Okay, thank you.
Yeah, thanks, Priya. Okay, so we'll move on to the second question. So that is from Sushant Bhatt. So the question is, will sun also become a black hole after supernova? So this question is for Jay. Yeah, over to you, Jay.
Thank you so much. That's a very interesting question. So, a sun is under general classification. The sun is considered to be a low mass star. And what happens to low mass stars at the end is that they eventually become something called a white dwarf. And this is what happens after an intermediary phase when the sun would stop, eventually at the end, stop the nuclear fusion reaction in its core, and it becomes a red giant and then at the end, the outer layers of these red giants are ejected into an explosion, and what is left is the core, and this core is called as a white dwarf, and this is essentially made of carbon and elements like carbon and oxygen and sometimes even helium. So, and black hole instead is black holes are the remnants of very high mass stars, which could be stars could be as massive as say 25 times or even more than the mass of our sun. So that's a difference between the sun at the end would end up as a white dwarf and not as a black hole. I hope that answers your question. Thank you so much.
Yeah, thank you very much, Jay. So we'll move on to our next question. This is from Shikhar. The question is in slide number 6, what is the full form of K as in temperature form? So the question is taken by Sandeep. So I hope I will be answering some on the other temperature forms.
Yeah.
Yeah, Sandeep.
Yeah, hello, Shikhar. It's a very fundamental questions, which is about the temperature. Like in anything, any quantity we measure in some units. So as you know that human body is in like, if you measure the temperature in degree Celsius, it is around 37 degrees Celsius. When you convert into in the Kelvin, it becomes around 310, which is mentioned here in the slide. So it's, and basically you can convert into Fahrenheit also. So it's basically a unit. K, the full form of K is Kelvin, which is given after the name of a scientist, which was a physicist as well as mathematician, was called Lord Kelvin, and he discovered many of the thermodynamical laws. And yeah, I think that hopes you. I hope that answered your question.
Yeah, thank you very much, Sandeep. So our next question is for Supriya. This question is asked by Neeraj Mangesh. So the question is, how much time does it take for a coronal explosion to reach the Earth atmosphere? Supriya, over to you.
Again, a nice question. Coronal mass ejections usually take 1 to 5 days, depending on how it interacts with the interplanetary medium and the solar wind, etc. So it's not like it usually take 1 to 5 days, but you, as you might know, like the light that is emitted from the photosphere will take 8 minutes, but coronal mass ejections are the particles. It's not the light that is coming towards us, but they are ions and electrons that are the material ejected from the sun. So this will, depending on how it travels, in which direction and what it encounters, it varies, and usually the prediction is to say 1 to 5 days after it is ejected from the sun. Thanks.
Yeah, thank you very much, Supriya. So our next question is from Vedant. So the question is, why is the sun expected to expand its radius in future? This question is taken by Jay. Jay, over to you. Yeah.
That's also a very interesting question, and it's $1 million question because this is the exact physics of this is not yet, I would say, at least in my opinion, not very well understood. So what exactly happens is, as I was talking also previously, answering a previous question, is after the fusion reactions come to an end in the center of the sun, if they at one point they would come to an end, while the elements like hydrogen or helium would still in the above layers would still continue to burn, and because of this, there we expect that this pressure is much higher, and this leads to the expansion of these outer layers, and this is when the sun moves on to the phase of something called as a red giant. But the exact mechanism of how this expansion occurs, in my opinion, it's still like a interesting study or a challenge that we need to understand better. So I hope that answers your question.
Yeah, thank you very much, Jay. So a related question is asked by Shikhar. So the question is, how fast is sun growing? In how many years will it become a supergiant? So I think this will be answered by Shubham. Shubham, over to you.
Yeah. So the sun is not currently expanding. The sun is, as we say, it's in equilibrium. So every stage of a star is dictated by equilibrium between two opposing forces. So you have gravity, which is trying to compress and collapse the star onto itself. And you have gas pressure, which is keeping gravity at bay. So because of that equilibrium, the sun is currently stable. But at the end of the hydrogen burning phase, as Jay explained to you, the sun will become a red giant. And when that happens, so the time scale for that to happen is we estimate that the sun has lived out currently around half of its life, and the lifespan of the sun is around 10 billion years, and it has already lived approximately half that life. So in another 5 billion years, a very long time to go, it will expand into a red giant. Thanks.
Okay, thank you very much, Shubham. I'll be taking the next question. This question is from Sachetas. So the question is, can you explain magnetic pole reversals and when could it occur on Earth? So this is very interesting, Sachetas. So on the Sun, the magnetic pole reversals happen every 22 years or so. So the North Pole becomes South and the South Pole becomes North. So this happens mainly because it's a combination of the differential rotation and Coriolis forces, other forces. So like Avijit explained, the convective motions and the differential rotation makes these fields pop up out of the sun. And then you see these dark spots on the sun, sunspots of concentrated magnetic fields. So these magnetic fields, you have positive and negative polarities. And out of which one of the there are opposite polarities on also, they are on the opposite direction on the northern and southern hemisphere of the sun. These polarities migrate towards the poles. One of those polarities migrates towards the poles and switches the polarity. All this process happens over 11-year cycle. So on Earth, so similar process, we don't have a similar process. We don't have differential rotation, and we don't have a similar process. Earth is a solid object as compared to the sun, which is a gaseous sphere. However, on Earth, there were theories that about 65,000 years ago, the poles were opposite side. The north was south, and the magnetic south was north. But there could be other reasons for that. I mean, in the recent news, if you have seen, there are news that the Earth's magnetic pole is moving. So the motion in Earth is mainly because of the molten iron core, which is there are different cells in this molten iron core which is moving, and because of those motions, the Earth's magnetic poles are moving. But this doesn't happen at the same scale as same time scale as that happens over the sun. So this might take like thousands of years for Earth's poles to switch. Yeah, I hope that answers your question. Sachadas. Yeah. So we will move on to the next question. So the next question is by Akash. So the question is, what are the advantages of using L1 point for solar observation? This question will be taken by Varun. Varun, over to you.
Yeah, hi Akash. Good question. I hope Abhijit has already explained that L1 point in space where combined gravitational forces of the two large body, in this case Earth and Sun, almost equals. So at this point we have several advantages. One of the advantages is that L1 provides uninterrupted view of Sun. So Earth does not come into the picture over there. So we have all the time uninterrupted view of the Sun. Another point is L1 is the nearest to the sun. Rather, it is nearest to the Earth, not sun. Sorry. L2 is also, but L2 covers, like L2 is between sun and Earth. Sorry, L2 comes in between sun and Earth. So L2 we can't have the solar observation. So we go at the L1. Another advantage is it has a very less fuel consumption because of the gravitational forces where it gets equal. So satellite uses very less fuel to be in the orbit. So these are the 2-3 points where we use solar observation basically at the L1. I hope it has answered your question.
Yeah, thank you very much, Varun. So the next question is by Hema. So the question is, what are the particles present in the sun? So this question will be taken by Avijit. Over to you, Avijit.
Thanks, Krishna. It's a very interesting question. So as we saw that Sun is basically a giant ball of plasma, which is, and plasma is nothing but ionized material, and most of the ionized material in Sun is hydrogen atom, and you have this electrons. And then we saw that the Sun converts hydrogen into helium. So helium is the next most abundant element. And then as we progress, helium is also converted into carbon and nitrogen and oxygen and other heavier elements. So we have small traces of these higher elements, but primarily the sun is consisting again of hydrogen, and then next is helium. And then you have all these electrons which are freely moving around.
Thank you very much, Avijit. So the next question is from Sachetas. So this question is, why does Earth's core rotation create a magnetic field for Earth? Could it be because of Sun's magnetic field? This question will be taken by Supriya. Supriya, over to you.
Hi. Earth magnetic field is not uh, because of the sun's magnetic field. It is purely because of the convective motions of the currents of, like Krishna explained before, because of the molten iron in the outer core of the Earth. This creates a magnetic field that is there around the Earth, but it has got nothing to do with the presence of the magnetic field or the sun. However, Earth's magnetic field is what mostly protects us from most of the times when from the particles that are coming from the sun towards us. Okay.
Thank you very much, Supriya. So I think we have many more questions coming up. So we will be answering. We will have please remember that we will have another question and answer session at the end, where we will be answering both solar daytime astronomy, nighttime astronomy, and also the career questions. So please keep sending in your questions, and we will answer further questions at the end of the session. Okay. Now we will have some nighttime astronomy talks. So over to the nighttime group.
Hello, am I audible?
Yeah.
Okay. Hi everyone, I'm Akanksha and I'll be talking to you about the nighttime astronomy. Uh, I'm sure you would have enjoyed the session on daytime astronomy and knowing about the sun, which is our nearest star. But at the same time, at night, when you look up at the night sky, you must be having a number of questions about what these where these stars come from and how they are formed, how they die. And if you have seen images from big telescopes, you would have also seen images of galaxies, and you would also wonder about where the universe came from. So to address questions such as these, I'm going to talk in this nighttime astronomy session. We are going to talk in three parts. The first part, we will talk on cosmology, where we will answer questions as on the evolution of the universe and how the universe was born and how it will end. In the second part, we will talk about galaxies, stars, and planets. We will talk about how galaxies were formed, how stars were formed, and how planets were formed. In the third part, we will talk about the instrumentation. That is, we will see how we observe all these stars, galaxies, and how we know what we know about the galaxies and stars. So, before before we go on to before I go on to explaining to you about the universe as a whole, like the first part is on cosmology, but I would introduce you to some basic concepts which will come in handy in understanding the latter part of this talk. So already Abhijit in his talk introduced you to the electromagnetic spectrum. So, what exactly is the electromagnetic spectrum? Is that whatever we see, all the light that we see, is in this wavelength range. When I say wavelength, it means the distance between these two peaks. So, the distance between these two peaks is what is known as one wavelength. So, everything that we see is in these seven colors or a combination of these seven colors. So, this is called the visible light. So, red is the highest wavelength and blue is the lowest wavelength that we can see. But there are wavelengths which are not in this visible light region. So if we go to even higher wavelengths, we need different kind of detectors. So that is the infrared. And if we go even higher, it is the microwave, and even higher is the radio wave. So radio wave is the same wave that you use for listening to your radio Mirchi or FM on your radio. And microwaves are the same waves which are used in your microwave ovens for cooking food. While on the lower side, that below blue, you have the ultraviolet, the X-rays, and the gamma rays. So X-rays are the same X-rays which, if you get a fracture, we use, but we cannot see them. So when we go to higher and higher wavelengths, we essentially go to lower energies. And when we go to lower and lower wavelengths, we go to higher energies. Now, there is one very interesting thing that you all must have experienced, especially if you've traveled in trains. So, if you are sitting in a train and there is another train which blows a whistle, and the moment it comes near you, you hear a beep sound, and that beep it dissolves later on. So that it becomes sharper and sharper, and it drops. So this effect is called redshifting. Similar effect we see in light. So what exactly is redshifting? So what happens is that if something is moving away from us, supposing it emitted blue light, but if it is moving and I am on Earth, this object emitted blue light, I on Earth will not see that it is blue. I will see it somewhere towards the redder side. That is, what I really see is that I see a larger wavelength. So this phenomena is called redshifting. The opposite thing happens when the object moves towards you. So the object may have emitted something in, say, red light, but what you will rarely observe is blue. So this is called blue shifting. So it happens across the spectrum. For example, if the object emits yellow light and it is moving away from you, then what you will rarely see is orange. But if it is moving towards you, then you may actually see something is green. So this phenomena is also seen in case of stars. So this is the spectrum. Spectrum means these are all the colors, all the wavelengths. Like Avijit said, if we pass it through a prism, so if we pass a starlight through a prism, we will see this, it split up into these colors. So if the star is moving away from us, all these lights will move red, redward. So this is called red shifting. So if you see, these distance between the peaks has increased. So this is called redshifting, and what happens is that wavelength of light increases in redshifting. So, so now I will proceed towards the main question, a very fundamental question that I suppose many of you would have thought about. So where did the universe come from? Where did you all come from? Where did the stars, the galaxies, everything came from? And I'm sure you would have seen these kind of pictures of galaxies, of innumerable galaxies, and countless galaxies, and what we can see as countless stars. So where did this all come from? And what do we know so far about the universe? So what we know currently about the universe is a very important thing that is called the universe is expanding. So there was this person called Edwin Hubble who in 1926 he discovered that galaxies are moving away from us, and it was inferred that every galaxy in the universe is moving away from every other galaxy. So what do we mean when we say the universe is expanding? So what we really mean is, so I'm sure you all would have seen a graph paper, right? This is like a graph paper. So each box in a graph paper is like 1 unit. Now this one box is 1 unit. Now supposing you increase the size of this box. So this is what happens in an expanding universe. So just imagine this to be a rubber sheet, and you make these squares on it and you just stretch that rubber sheet. So the expanding universe means that the underlying space is expanding. So similar thing happens in the universe. So if this is one galaxy and this is another galaxy, so as you see, when this rubber sheet is expanding, these galaxies are moving away from each other. So why they are moving away from each other? Because this sheet is expanding, because these boxes are becoming bigger. So what other thing will happen is that if it is expanding, then every galaxy, for example, if I am here, then I will feel that this galaxy is moving away from me. If it is moving away from me, then the light that is coming from this galaxy will be redshifted. So if this galaxy is emitting something in bluer side, by the time it reaches here, it turns red. So this redshifting is what Hubble had found. And using this redshifting from distant galaxies, he inferred one more thing. So what he found was that the more distant a galaxy is, the faster it is moving away from us. For example, this is NGC 55847. In this plot, these are different galaxies. These are actual galaxies. And in terms of distance, this galaxy is the farthest away from us. So this distance is increasing in this direction and velocity is increasing in this direction. So what he found was that the more distant a galaxy is, the faster it is moving away from us. And the closer a galaxy is, like this galaxy, NGC 58666 is nearer to us, the slower it is moving away from us. So this was a very profound discovery, and it revolutionized the way we look at the universe. So so what do we know about the universe today? So we know that so you will be really amazed to know that all of the universe that whatever you know, whatever you see, you, me, I, stars, galaxies, all the ordinary matter that we know of, that is all that just constitutes about 5% of the total elements in the universe. So we are just 5% is normal matter. Rest of it, what it is, we do not know. We know that it should be there through indirect methods. We can detect them. We can detect dark matter, which is 27% of the total energy budget of the universe. So 27% is dark matter and 68% is dark energy. So how do we know that there is dark energy, for example, is again, we use supernovas and we use distance measures using supernovas to infer that there is dark energy, because the effect of dark energy is to accelerate the universe. So the velocity with which the galaxies are moving, if that velocity changes, then it is acceleration. So it couldn't have happened if there was no dark energy. So this is how we inferred that there has to be 68% dark energy. But how do we know there is dark matter? So there were some scientists like Zwicky, Ford, and Vera Rubin who answered this question, that who inferred that there should be dark matter. And how do we know that? We know that from something that is called as rotation curves of velocities. So if you notice here in this plot, this white line, so this is velocity and this is radius. This is a galaxy, and every star in the galaxy is moving about the center of this galaxy. This radius is the distance from the center of the galaxy. So what we expect from known laws of physics is, as we go outside from the center of the galaxy, we expect that the velocity of the stars on the outskirts should decrease. This white line is what we expect from theory. But what we really observe is this green line. When we actually measure the distance, the velocities of stars at this different radii from the center of the galaxy, we find this green plot, which means the observed velocity is more than the expected velocity. And the only way we can explain this extra velocity is by proposing that there is extra matter out there which we cannot observe, which we are not able to observe, but it is still interacting with the ordinary known matter through gravity. So this is how we know that there is dark matter in the universe. So like I already mentioned that the expansion of the universe is a very important phenomena. So why it is important? So what exactly happens is when the universe expands, what happens? The volume increases. When volume increases, the density decreases and there is a corresponding decrease in temperature. And if the temperature of an object decreases, then the energy also decreases. Now, every physical process requires certain amount of energy. For example, if you want to form protons, if you want to form atoms, then you need certain amount of energy. And the heavier an object you are forming, the lower energy you need. For example, if you are forming atoms at a higher energy, they cannot form. The atom will break at higher energies. So same phenomena is happening here when the universe evolves. So let me just give you a timeline of what happens. So you all must have heard that the universe, it started in a Big Bang. Now, what really is a Big Bang? So Big Bang is not really bang in the sense of an explosion. It's not like something exploded there. So Big Bang is just a point in time in the history of the universe where the density is so less, the density is so high, it is infinite. So all the known laws of physics, they break down. So that point in time and space, we call it as the Big Bang. And this is where we start our timeline of the universe. So the universe, if it started in a Big Bang, then after about 10 to the power of minus 36 seconds. So what this means is 10 to the power of minus 36 seconds means 1 divided by 10 followed by 36 seconds. So after about 10 to the power of minus 36 seconds, the universe entered an era which is known as inflation. So inflation, you would have heard many times this word. So inflation just means there is an expansion, there is an abrupt expansion. So the expansion of the universe is so abrupt during this time that in a matter of about 10 to the power of minus 26 seconds, the universe grew from the strand of a hair to the size of our galaxy. So to give you an idea of how much it expanded in how short duration, when you blink your eye, it's just 1/10 of a second. So imagine it is 1 divided by 10 followed by 26 zeros. In that small time, it expanded by the diameter of the strand of a hair to the size of a galaxy. So this fast expansion did one more thing. So the universe, on an otherwise smooth universe, it introduced tiny ripples on space-time. So these tiny ripples are what, as we will see, these tiny ripples later on grew into all these stars, galaxies, and all the structures that we see today in the universe. So this happened in a very early stage of the universe. After about 1 second, so if you notice now the temperature is decreasing. After about 1 second, the temperature was conducive enough for protons, neutrons, and electrons to form. But still, the universe is still pretty hot for all of them to combine and form atoms. They are all still separate. There is protons, neutrons, electrons, and since their temperature is very high, there is also light. Light meaning there is photons. So this protons, neutrons, electrons, and photons, they all form a plasma and they all are interacting with each other. So what happens after that, at about 10 seconds to 20 minutes, the temperature is about 1 billion degrees Celsius. At that temperature, protons and neutrons can begin to combine and they can form nuclei of atoms. But remember, electrons are still free. And since light interacts more with electrons, the light is still interacting with electrons. So now what we have in the universe is nuclei, light, and electrons. So all of them are in one soup, they constitute one plasma. So it's like an ionized hydrogen atom. When you will ionize a hydrogen atom, what will you have? You will have the nucleus of hydrogen and you will have electrons separately. What happens after about 380,000 years, when the universe is 380,000 years old? So this is a very interesting epoch because this is the furthest we can know about the universe through direct observation. So this is the time when the first atoms formed. Now these electrons are no longer free. They have got bound to the nuclei and the first neutral hydrogen atoms have formed. But now there are no free electrons, so light can no longer interact with matter. So this light has got disconnected, so it evolves on its own while the rest of the matter evolves on its own. And this light, because the universe is expanding, it redshifts, and today we see it in the microwave region. So there are satellites that are sent up in space, and we can still today detect this cool down radiation right from here. That is about 380,000 years after the Big Bang. And using this light, we can infer whatever must have happened before that. Since in anything at any epoch before this, we do not have any direct proof. Now, what happened when the universe was 1 billion years old? So when the universe was 1 billion years old, the first stars and galaxies, they began to form. So when the first stars and galaxies, they started to form, what they started to do was they ionized these neutral hydrogen atoms. All the radiation that came out of these first stars and galaxies, they ionized the neutral hydrogen atoms around it. Now, where did these first stars and galaxies come from? So those tiny ripples which were there in the beginning, they grew into the first stars and galaxies. So I will come to this ripples later on. So now coming on to today, what do we see today is a universe which is full of galaxies and stars, and it is 13.7 billion years after the Big Bang. The temperature of the universe has dropped down to minus 270 degrees Celsius. The temperature of the universe has dropped to minus 270 degrees Celsius, and all the other heavier elements have been formed inside stars. So whatever constitutes you, me, everything is formed inside stars. And this is the map of the cosmic microwave background. So this is the cosmic microwave background. And this is what we use to infer everything that happened in the universe before before this epoch, when the first neutral hydrogen atoms they formed. So now coming on to what these ripples really are. So give you an idea of what exactly these ripples are. So so you have so what when I say there are ripples in space time, it's something like this. You know, you have a sheet. Again, you have a rubber sheet, and wherever there are ripples, the matter will fall into it. It's like it's like a shallow well. So matter will start falling into it. So where do what do I mean by that? Supposing you have a lighter object and a heavier object, so the ripples will be different. When you will drop many such objects, they will all leave their impression and it will get frozen out. This frozen out ripples are what we see in the cosmic microwave background map. So this cosmic microwave background is these fluctuations that you see are basically temperature fluctuations. The blue and the green regions are something like higher and lower temperature regions. So it is these ripples that we see in the cosmic microwave background map. And this cosmic microwave background was discovered in 1978 by Penzias and Wilson. It was an accidental discovery because they were just testing a microwave antenna for wartime, for war purposes, for army. And what they really found was that there was a constant extra radio source which they could not trace to anything. In fact, at one point they even thought that it was due to the pigeons. They even cleaned the antenna and still they could not infer where this is coming from. Later on it was found, it were the theorists, they found that it was due to the cosmic microwave background radiation, which is coming from all directions, and it has now cooled down to about 2.7 degree Kelvin, which is around minus 273 degrees Celsius. So what is the importance of all this, of studying all this is, so if you have noticed that we have encountered energy scales and time scales which we do not encounter in our day-to-day life. Now all the fundamental physics that comes in by studying the evolution of the universe allows us to answer questions at those time scales. So this is what we call as
I guess we have lost Akansha. So probably I will continue from here. Hi, I'm Vidisha. So Akansha was just mentioning about the ripples that we saw in the previous slide and the cosmic microwave background radiation. So like I have a small video to show you what happens. So beginning from today, like you see stars, galaxies that you are seeing today, but how did they come? Like because of those ripples that were there, they formed high density regions, and with time, like you can see in the map, that these cold regions, they clumped, the matter clumped into them, and they became denser and denser, and with time, those dense regions, they formed stars and galaxies. So today, and in like they became heavier dense clouds, and inside those clouds small stars formed, and all these things happened. So this is basically what was the story about like the journey of the universe, like how things started from a small point and the universe expanded, and your atoms, nuclei, and everything formed, and currently we see stars, galaxies, and planets. So yes, I would ask Jay to speak next about who will tell you about galaxies, stars, and planets. Jay?
Oh, thank you so much. I'm just sharing my screen. So a quick question, are you able to see my screen as well as can you hear me well?
Yeah.
Perfect. All right, so thank you so much. And after that wonderful talk on cosmology, we now move on to our next section, which is on galaxies, stars, and planets. So the first thing that might come to your mind is like, how do these galaxies look like? How do they appear to us? So in general, we can see there are elliptical galaxies. Then there are galaxies which have a spiral-like shape. And then we also have galaxies which do not have a particular structure, so they're called irregular. So based on their appearance, Edwin Hubble gave us this so-called tuning fork diagram. And here you can see at the handle of its fork, we have the ellipticals, or the elliptical galaxies, while on the top prong, you see there are galaxies which have a bulge in the center, and they have spiral-like arms. So these are called as normal spirals. In the bottom prong, you see that these spirals sometimes can also have this additional bar-like feature, and these are called as barred spirals. Now you may wonder, why do these galaxies have different shapes? So imagine if the giant molecular cloud that is responsible for forming these galaxies, initially, if this cloud was spinning very fastly, or it had a high angular momentum, in time, it would gradually contract and also evolve and flatten out, and it would give rise to something called a spiral galaxy. While if this initial giant molecular cloud of gas and dust is not spinning much, or has a slow spin, or is just not spinning at all, it was in time collapse in time, contract in time, and would give rise to an elliptical galaxy. A galaxy is also host to billions of stars. So now let's see how these stars are born, how they evolve in time, and also how they die. So starting from the first stage, we call birth. The stars are formed in these giant molecular clouds of gas and dust, primarily made of hydrogen along with other elements and molecules. And these giant clouds are called as nebulae. And here you see an example of a nebula, which is called as the Butterfly Nebula, and it has these beautiful butterfly wing-like pattern. Here is another example of a star-forming region called W33, and here in the center you can see that there are these formation of these yellow balls, which would eventually contract and form stars. So to better understand the star formation process, let's go step by step. So essentially, as I was talking about, first we have this giant molecular cloud that's coming together because of the gravitational force. Inside this giant molecular cloud, you have these local high-density clumps and cores that begin to form. And in time, these clumps become denser and denser, and they form the initial step or the phase, which are called as protostars. So we have these multiple protostars forming in these clouds. And then these protostars also accumulate matter around them, and they form something called as disks. So they have these disks we find, and then eventually these disks are the source of the material that ends up as forming planets. Is that what we see? And here is an artist's impression of how a protostar looks like along with the disk. And this is what I would like to call the baby phase. So next on the list is the main sequence. And before that, let's talk about what kind of stars can be formed from the protostars. So taking the reference of the sun as 1 solar mass, which is 2 times 10 to the power 30 kilograms. A star is a low mass star when it has mass roughly less than 3 solar masses. We can also call a high mass star, which when it has a mass roughly between 3 to 25 times the solar mass. And a very high mass star is a star which has mass much greater than 25 solar mass. So going back to this diagram, so depending on the mass of the star, there is a split in this evolutionary trend, and the low mass stars follow the upper trend, while the high mass stars follow the lower trend. So as Abhijit was also talking about earlier, in these protostars, when they go denser and denser and become hotter and hotter, and there is at some point there is a ignition that turns on the nuclear fusion reactions, and these are basically when the hydrogen atoms combine to form helium atoms, and in this process a lot of heat and temperature energy is also generated. So this is what you see on the diagram on the left. On the right, you see something called as a Hertzsprung-Russell diagram, which classifies different stars based on their temperature, as you can see on the x-axis. So the cooler stars on the right and the hotter stars are on the left. And depend also on their brightness, which is depicted on the y-axis. So the brighter stars are on the top, while the fainter stars, as they appear to us, are below. And when the star starts these fusion reactions, it enters the so-called the main sequence of this HR diagram. So like Abhijit also mentioned earlier, the sun is currently in the process of burning, going on these fusion reactions right now. So it's also a part of the main sequence. And this phase is what I would like to call the adult phase, where you have a lot of energy and you're producing energy. Moving on, the next phase is called the giant phase. So as one of the questions that also came up earlier, what happens when a low mass star like our sun, the fusion reaction stopped in the core, but the fusion reaction that's still taking place in its outer layer. So because of the radiation pressure, the envelope of the star begins to expand slowly, and the star begins to swell. And this is when it enters the red giant phase. So the main sequence star, like our sun, when it becomes a red giant, hopefully in another 7 billion years, it would expand to a bit more, a factor of 100 times. So to give you an idea of the comparing different sizes, so we have your sun here as a tiny spot, and while we have a red giant, Aldebaran, which is about, say, 100 times or a bit more than the size of our sun, while we have these red supergiants called Betelgeuse or Antares, and they are essentially formed by a high mass or very high mass stars. So this is the phase I would like to call getting old and fat phase. Next on the list is sadly death. So what happens is when the fuel also runs out in the outer layer as well, and the fusion reactions are getting to a stop, the outer layers are ejected very rapidly, and it's sort of in an explosion sort of a way. And when a low mass star like our sun would shed out its outer layer, it would lead to something called as a planetary nebula. And here, these are the different planetary nebulas that we see in sky. And for an example, this Helix Nebula, or my favorite here is the Hourglass Nebula, which has like the hourglass-like structure. For a very high mass star instead, this expulsion of the outer layers essentially leads to a catastrophic explosion, much more powerful and energetic, and this is called as a supernova. And here you see that there are different the material ejected out leaves all these remnants around. So these are all the different pictures that you see here are the different supernova remnants. And for example, this Crab Nebula is a supernova remnant about 600 light years away from us. So what do I mean by a light year? So a light year is a distance measure used in astronomy. And 1 light year is equal to the distance traveled by light, which is at the speed of 300,000 kilometers per second, and how much distance it covers in 1 year. So when you multiply speed by time, you get the distance, and this distance is 1 light year, and 1 light year is roughly 100 trillion kilometers. So this Crab Nebula is about 600,000 light years away from us, or 6,000 light years away from us. Another question that might come to your mind is how frequent are these supernovas? So in our galaxy, Milky Way, which has the length roughly about 50,000 light years, the frequency of a supernova to happen is about 1 in 100 years. Another question that might come to your mind is how can we be affected by such supernova? Are they dangerous to life on Earth? So imagine if there is a supernova happening about 300 light years away from us. The chances of it is happening, or the probability of it happening, is 1 in a million years. And even if such a supernova happens, the effects might not be strong to affect to have a major impact on life here on Earth. So for now, I think we are safe for a few years, at least a few hundreds of years. And this phase is what I would like to call the blow-up phase. Moving on. So the last stage of the star is a remnant of what is left behind, the dead star. So a low mass star essentially forms a white dwarf. This was also a question before that was asked. And so a sun would eventually end its life becoming a white dwarf, that's what is expected. A high mass star would become a neutron star, and a very high mass star would end up as a black hole. And this is what I would like to call the skeleton phase. Now, white dwarfs essentially are the remnants of the low mass star, and the cores are made up of carbon, oxygen, sometimes helium, and the electrons of these atoms help to provide the pressure required for in order to prevent the further collapse of the structure due to gravity. And the size of white dwarfs are more or less the size of our Earth. And here on left, you see that a sun-like star would go a red giant phase and would end up like a white dwarf. So this is how an HR diagram would look like for a sun-like star. Now, next is a neutron star, which is a result of a high mass star. And these are made up majorly of neutrons. At least 80% of the matter inside neutron stars are just neutrons. So that hence the name. And they have masses about 1.5 to 2 times the mass of our sun, but their diameter is only 20 to 24 kilometers. So this is essentially the size of a city. So imagine all that mass just encompassed in such a small region. So hence, they're one of the densest or the one of the compact objects that exist in nature. And when you take a piece or a pizza slice of the interior of a neutron star, then you also find that it is made up of different layers of different densities, just like also we see in the sun. And in one of the layers, one interesting fact is that you see these pasta-like phases of when the neutron stars and also, when the neutrons and along with the protons, they make these pasta-like structures called spaghetti or lasagna. Now, the neutron stars are also objects with one of the strongest magnetic fields that we see in the universe. And if this neutron star is spinning along its magnetic field axis, sometimes what happens is you can see the radiation coming from along its poles. And if this radiation can be detected on Earth, we see them as pulses, just like how you see in this movie above. And this is then they're also called as pulsars in that case. The last, the remnant that we have is when the very high mass stars collapse, and these are called as black holes. And a black hole in general is the gravity in the black hole are so around, and in fact inside also the black hole is so strong that even the light cannot escape from them. But the black holes are very simple natures in simple objects in nature because they can be described by their mass and simply their spin, and sometimes also charge. So we just need these 3 characteristics to describe a black hole structure. But interestingly, what is inside the black hole, the internal structure, is still not well known. But what is thought is that in the inside, in the center, the density is so high, it almost tends to infinity. And the laws of physics break down, and we have something called as singularity. Also, last year, we had the first ever direct picture or the image of a black hole. And this is a supermassive black hole in the center of the galaxy Messier 87. And here you see the light coming from the disk of the black hole, while the black hole is situated in the middle. A supermassive black hole is a black hole that has the mass of about 10,000 times or 1,000,000 times the mass of a normal black hole or a stellar black hole. Another interesting phenomena that we see in nature is gravitational waves. So when these compact objects, black holes or neutron stars, are in a binary system and they go around each other and they merge, they produce something called as ripples in space-time. And these ripples are called as gravitational waves. And these waves were first predicted by Einstein in 1915 and only detected 100 years later directly, caused by the merger of 2 black holes. And this was detected using a technique called laser interferometry by LIGO-Virgo detectors. Moving on quickly to the last section is the planets and how are they formed. So recalling the phase when we had this protostar and we had a disk around it. So gradually in time, the material in the disk condenses and cools down to form these planetesimal blobs. And eventually in time, these blobs act as fundamental building blocks for forming the planets. And one of the main fields in astronomy is to find these planets which are orbiting around other stars, and these planets are called as exoplanets. And until now, about 4,000 of them have been already discovered. And a few of them also have characteristics which are potentially habitable and similar to Earth. So there is indeed a high probability that we are not alone in this universe. So now to understand better how we see or observe these different astrophysical objects like galaxies, stars, and planets, we move on to our next section on instrumentation. So over to you, Ramya.
Hello everyone. Till now you listened about how universe started and then what are the objects we can observe in our night sky. So in this session, I'll introduce you to how we are going to make these observations or measurement or what kind of instruments we use. So as Akanksha explained to you before, most of the astronomical sources in the sky, such as stars, galaxies, etc., they emit in the entire electromagnetic spectrum. That means from gamma rays you get till the radio waves. So, but the problem is only some of these radiations reach the Earth, and the remaining are blocked by our atmosphere. So, if we want to make any observations or take images in different wavelengths, we have to go beyond the atmosphere. Like why do we want to observe the sources in different wavelengths? In the right corner picture, if you see, when you look at a galaxy in different wavelengths, you can see that it highlights different features in the galaxy. So if you want to study any of the source completely, you want to make multi-wavelength measurements. That means you want to take its images or its spectra in different wavelengths, and in order to understand what is happening in it. So among the entire electromagnetic spectrum, only the optical window, that means the visible light, and the radio waves reach the Earth. But if you want to make measurements in any of this, that such as X-ray, ultraviolet, gamma rays, you have to go to space. So that is why we have two different telescopes, that is one ground-based telescopes and also we have space-based telescopes. So for the basic analogy, what is a telescope? It is nothing but it is nothing but an analogy as a bucket. If you have a smaller bucket, you collect less amount of water. You have a bigger bucket, you collect large amount of water. So telescopes work with the same analogy. You have a smaller telescope, you collect less photons, and you have a bigger telescope, you collect more light. In the telescope, like I said, that you want to measure, you want to take images in different wavelengths. Your telescopes are designed in a different way for different wavelengths. For example, for the optical window, the window which we get to the ground, in this case, these telescopes are made of either lenses or mirrors. They can be combination of a convex and concave lens, or they can be concave and convex mirrors, which you would have studied in your school. But the most of the telescopes, that is large telescopes which we have today, are mostly mirror based telescopes because it's more easier to manufacture a mirror compared to a lens. So this is the case for an optical telescope. So how do you make a radio telescope or an X-ray telescope? In the left figure, you can see the radio telescopes would be nothing but a dish antenna, which you would have in your houses, you would have seen. So this is the way the radio telescope is designed. And in the right side, you can see that is an X-ray telescope. So the basic principle of working, that is collecting the photons, is same for a telescope, but the way you design it is different for different wavelengths. So in the case of the telescopes which are on the ground, such as for optical or radio telescopes, where are you going to put them? Because X-ray or UV measurement you're going to launch it to space. But in the ones which you're going to put on the ground, where do you put a telescope? So telescopes are usually put far away from the city because you want to avoid light pollution. What exactly is light pollution? If you go out and look at the night sky, you see very less number of stars, but you have lots of light around you. Once you go far away from the city, you will be able to see more number of stars, which means you have less light pollution. So in the case of telescope, we want to observe more stars. So we choose a location which is far away and it is preferably high altitude and dry air. And once you have the telescope, it is usually, you can see in the middle of the figure that there is a dome. So the telescope is usually protected by a dome, and the dome opens. And on the left side is the telescope which is sitting inside the dome. So these telescopes rotate and point to the object for which you want to take the observation. And in the same figure at the bottom in the blue box, you see those are the instruments you place in the telescope, because your telescope just collects the photons. So it is the instrument which makes up a data which is going to be useful for your research. So these instruments can be either an imager or a spectrograph or a polarimeter. What is an imager? Imager is nothing but your the camera which you use. You look at the object and you just click the photo and you get the photo. In the same way, at the focus of the telescope, we place an imager which is similar to this chip, which is called a CCD or a CMOS device, and you take the image of the night sky. And this is how the image of the night sky looks like. So the next thing is you want to understand what it composes of. Like you are looking at a star or you're looking at a planet. You want to know what is it, what elements are present in it, what molecules are present in it, what is happening in it. So in order to do that, we use spectrograph, which is basically a prism. When you put a prism in the sunlight, you see you see the dispersion and which splits into the entire visible wavelength region. In the similar way, you use a spectrograph based on the prism in order to understand what elements are present in these astronomical sources. So these are the main two instruments which we use in all the observatories, that is, you make an imager or you have a spectrograph. So how it is used, like how you can understand by the data is, I am going to give you an example. You all have heard that we detect a lot of exoplanets. So how do we detect it? And because these are the two instruments we have, so how do we make the detection? If you look at the left figure, you see a yellow color star, and there is a black dot which is passing on the yellow color star. So just observe carefully what happens when the black dot passes through the yellow color star. There is a dip in the brightness. You can assume it as an analogy to what happens during a solar eclipse. When the moon blocks the sun, you don't get to see the sunlight. So in the same way, when the planet moves in front of the star, it blocks some amount of the light from the star, and that is how you get to detect that there might be a planet around the star. So what you do in the observation is you take series of images, like using your imager, and you start comparing the total amount of light or the flux which is there in each image. If you see that there is a reduction in the flux, that is when you know that, okay, there is an exoplanet. The second way of detection is by using the spectrograph. This movement of the spectra, the red shift and the blue shift, Akanksha already explained in her talk. So what happens is when you're taking the spectra of the star and the planet moves along with it, though you see a spectra moving in one direction, and when planet goes behind it, you see the spectra moving in the other direction. So if you are continuously recording this spectra for a longer period of time, you will know that there is a presence of a planet. So this is how these instruments are used to detect an exoplanet. So this is only one of the examples. And the second one is in the case of radio telescopes. You all might have seen the image of the black hole. So this image of the black hole was made from using the radio telescopes. And it's not just one telescope, it was a network of the telescope all over the globe. So at the bottom, you can see various radio telescopes located at different parts of the world. They all collected the data and then they processed the data and then they could make the image. So it is not always like one telescope is going to give amazing results. We also have a network of telescope which work together in order to give good results. So what are the next challenges we are facing in astronomy? Like what are the next decade instruments or the telescopes coming up? So as I mentioned to you that when you have a bigger telescope, you collect more light. So what happens is you want to have bigger telescope because you want to see the sky deeper and deeper. So in the next decade, we are building three large telescopes. One is a 30-meter telescope, Other one is a Giant Magellan Telescope and a European ELT telescope. They are all 30-meter class telescopes. So what we can assume is, so we have a very big telescope, we are going to collect the data, and we will have very good high resolution images possible. But we also have a challenge when we come to that, because what happens is when you have observing any star, the light of the star passes through the Earth's atmosphere. So when it passes through the Earth's atmosphere, the atmosphere disturbs the light coming from the star. So because of which, however the star is there, we don't see the exact image. We see a low resolution image, you can call it. But you can see in the left side, I'm showing you the comparison of the two images. The left one is an image taken from a 0.7 meter ground telescope, and the right one is taken from a 1 meter space telescope. That means which is beyond the atmosphere. So if you want to get very high resolution images, one solution is you go beyond the atmosphere. But is it possible to construct a 30-meter telescope in space? No, it is going to be so difficult and it is going to be so expensive. So there are two options to it. One, you launch a space telescope, or the second thing is you try to see how you can remove this problem which the atmosphere is creating. So in the next decade, we also have a space telescope, so that we are removing the problem of the atmosphere. That is, we are launching the James Webb Space Telescope in next few years, and the size of this telescope is 6.5 meters, which is compared to the Hubble telescope of 2.4 meters. And so if you don't want, in the case of all these large telescopes I showed you, we cannot launch it. We are going to build it on the ground. So how are we going to overcome the problem of atmosphere? So that is what this video shows. You can see that when the source is emitting the light, the right side shows the actual image of the source. But whereas when you come to the telescope and take the image looks like a very low resolution image. So how do you correct it? You use a technique called as adaptive optics and try to create the disturbance what atmosphere is creating and try to correct for it at your ground level. Wherever you have the telescope, you have another instrument called adaptive optics instrument, which corrects for this aberration, so that you can get the high resolution images even on the ground. So the two options are, one, you go to space, or you have a very good adaptive optics system to get good images. So what are the next thing is, in these mega projects, whatever I mentioned, what are India's contribution? The 30-meter telescope, which is going to be built in Hawaii, India is manufacturing some of the segments, that is mirror segments. So I told you the size of the primary mirror, right? So the primary mirror has so many small mirror segments. So India is going to manufacture that, and also it is going to design and build two spectrographs. The spectrograph I explained to you using a prism-based or grating-based spectrograph. So India is planning to build that. And the other project which India is involved is Square Kilometer Array, which is a radio telescope. And the third one is a gravitational wave, which you all know. So India is also is involved in the gravitational wave observatory. So at the end, if you are interested to pursue your career in astronomy, you have options. If you take up any of these fields, you can take up optics, electronics, mechanical, or software. All these things would be useful in the next 15 years in the field of astronomy. Thank you. You can ask questions by using the form which has already been told to you. You just go to the link and type your questions in the nighttime astronomy questions and just submit it.
Okay, so we move on to the question answer session now. So let's start that with the first question. The first question is from the first question is by Rohan for Sandeep, and the question is why aren't the faraway stars in the night sky, which when seen from the naked eye redshifted? Sandeep?
Yeah, it's a very good question. So as we know, the star emits light in all over the range of the broad spectrum of electromagnetic spectrum, which Akansha talked about. And so the redshift will depend upon the velocity of the star. So how far it is moving towards us, or it is moving away from us. So with the naked eye, we cannot see the small changes in the wavelength, because the light at which the wavelength at which star is emitting will be different when it is moving. So it will be very small difference, and it cannot be observed. You cannot measure it with the naked eye. It means like you cannot see the light turning from blue to red in the visible range, because it's very small change. So either you need to take a spectrograph, uh, like dedicated observation for this. You cannot observe with the naked eye. Thanks.
Thank you, Sandeep. The next question is for Arun by Ushasi Roy Chaudhary, who wants to know how fast is the universe expanding, and will it keep expanding for all eternity?
Thank you, Shivam. Yeah, that's a good question. The rate at which the universe is expanding is characterized by a parameter called as the Hubble's constant. Although there is a debate in the scientific community as to the exact value of it, it's roughly about 70 kilometer per second per megaparsec. What it means is that if you have a galaxy which is 1 megaparsec away, it will be moving away from us with a speed of about 70 kilometers per second. So that is what characterizes the rate at which the universe is expanding. Now, whether the universe will expand forever, that again depends on the possible eventualities and the fate of the universe. One possibility is that the expansion of the universe might slow down because of the collective gravity, and all the galaxies might collapse back, which we call as a big crunch scenario, which seems to be highly unlikely with the current observation. But what we do think is that the expansion will continue. The galaxies will drift apart. Whether they will drift apart with a constant rate or whether the acceleration that you see today keeps increasing is still up for debate, and observations are going on. Thank you.
Thanks a lot, Arun. The next question is by Rohan for Saili, who wants to know, does every galaxy have a black hole in the center? Saili?
Yeah, hi Rohan. As Jay explained in the beginning, how there exist stars of different sizes, there also exist black holes of different sizes. Although we cannot observe them directly because of their because they're so highly dense, they attract all the matter towards them, including the light, and nothing can escape them. Although we cannot see them directly, we can see their effect on the surrounding, stars or gas or clouds and material surrounding the black hole. So, having been observed those things in galaxies, scientists scientists have long believed that the black holes of various sizes may exist in the centers of almost all galaxies. Some might be stellar mass black holes, some might be supermassive black holes. But yes, the belief is that this black holes exist in almost all the centers of all the galaxies. I hope that answers your question. Answers your question. Thanks.
Thanks a lot, Saili. The next question is for Jay by Vanshika, who wants to know, what do neutron stars fuse to produce light and heat? Jay, you want to take that?
Thanks a lot. And it's also an interesting question. And perhaps I forgot to cover this during my talk as well. So what happens is when a high mass star ends up as a neutron star through a supernova, in the core, which is a neutron star, there is no more fusion reactions happening. So there is no more atoms combining each other and producing energy. So what gives the temperature? So when this supernova happens, the temperature of the neutron star is about 10 to the power 11 or 10 to the power 12 Kelvin. But then there is no further energy production in this neutron star. So it eventually cools down in many years, and it becomes by emission of neutrinos from its within the cores, within the internal layers. and it reaches about 10 to the power 6 Kelvin in a few hundred or thousands of years. And this is what we also call as the cooling of neutron stars. So they cool down eventually, and they're not producing energy. I hope this answers your question.
Thank you, Jay. So we'll take one more question before we move on to the next session, which is career. But in case your question hasn't been answered, we'll come back to these questions at the end. There's a general Q&A session. So the last question before we move on to the next is for Swagat by, so this question is by Neeraj for Swagat. And the question is, could there be more than one universe? Swagat.
Hi. So the question could be answered based on what we mean by more than one universes. What we know for sure is that there are there are more parts of our own universe outside the boundary that we have seen until today. So if we wait for a few billion years, we will see a little more. However, it's a genuine prediction of theories of early universe that due to the action of quantum mechanics, our universe could have, it's highly possible that our universe could have some kind of an island structure. Like imagine an island in a, there is ocean and there are many islands. Each of this island is like a universe. It has its electrons, protons, and some of them are atoms, some of them have life, planets. And the water part, which are in the analogy, the water part is a empty space which is exponentially expanding. So these islands are being constantly created in this empty space, and they're being pushed apart from each other due to the expansion of space in between. So that's first thing that's quite possible. Second thing, that's actually predicted by some of the fundamental theories of physics in the early universe. So in that sense, there could be more than one universe. If you call these pockets as universes, then.
Thanks a lot, Swagat. So now we move on to the career section. And Sandeep, could you take over?
Yeah. So yeah. So as you have heard, what all the objects in the sky, and what are the challenging questions in the daytime astronomy as well in the nighttime astronomy, like in the daytime astronomy, how the corona gets heated up, and in the nighttime astronomy, how our universe originated, and we have many more questions which are still unanswered. And if you have passion towards astronomy and you want to build a career in astronomy, and in a way that you can contribute to these questions, then I will take you through this journey, how you can how you can make a career in astronomy. So in astronomy, apart from seeing the sky, whatever we observe, we do mainly three kind of, here we have divided into three categories. Like first category is we do theory and simulations and modeling, in the sense like whatever we observe, we want to explain whatever we observe in terms of physical modeling, what is the physics behind this and that. And then we also would like to simulate whatever the present universe we see, or you want to simulate any object in the sky. So you need to do you need to solve the equations, and you can solve the equation in theory with the pen and paper, but everything cannot be done with the pen and paper. Then you need to have computers which can solve harder equations, and that's why you need simulations. And then you also can model some phenomena, and that's what we do in the theory and simulation modeling part. And then in terms of observations and data analysis, which is the, like, astronomy is the branch of physics which is like most of the things are done observationally. You cannot do you cannot do much of the experiments. There are still few experiments, but the most of the things which we deduce is by observations. And this for observations, you have seen the telescopes which are mentioned in the earlier sessions. Like for sun, you have various dedicated telescopes in India as well as in abroad. And for nighttime astronomy also, you have several telescopes which are ground based as well as the space based telescopes. And to observe to observe any object, you need to write proposals, and which will be checked by expert whether it's necessary to do observation for these objects or not. So yeah, this is in the observation section. And then you can also contribute to the instrumentation part, which is the building of telescopes, which Ramya has mentioned in the last session. And there also you can contribute in the optics, mechanics, electronics, electrical. So there are many more opportunities in this part as well. So after your 12th standard, if you want to proceed with the making a career in astronomy, so suppose if you have physics background, if you want to do bachelor's, you want to, there are three main branches through which you can go. So one is the bachelor's. If you have bachelor's in your physics, or sometimes mathematics people also can go in this pathway. So you can go with your masters, and then you can continue if you give these exams, like just gate net and institute exam. So in through these exams you can get admission for PhDs in India. So there are several universities and institute which takes admission through these exams, and I will mention some of them in my next slides. And then if you have your bachelor's in engineering or electrical, or you have say BTech, so basically engineering background you have, then you can take admission in your MTechs through GATE, and then you can opt for the PhDs in astronomical instrumentations. And another way is like, so if you have if you have bachelor's in uh, engineering and mechanics, then you can also take admission through GATE as well as just both. So if you have still background in the engineering background, so you can still pursue PhD in astrophysics and astronomy apart from astronomy. So let's see, there are many universities in India which offers masters in astrophysics. Like you have Delhi University at the heart of the India, and then you have Pune University in Pune, Maharashtra, and then you have IST Trivandrum, and then you have St. Xavier's Kolkata, and then you have IIT Indore and Andhra University, Osmania University in Andhra Pradesh, and then you have Anna University in Chennai. So these are the universities where you have a dedicated master programs for astrophysics. Apart from this, there are many institute which are very dedicated institute for PhD programs in astrophysics. So let me start from the Gujarat, where you in Ahmedabad you have PRL Institute, and then if you come slightly lower part of India, there is Mumbai. You have TIFR, which is the Tata Institute of Fundamental Research, and then in Pune you have two of the good institutes of India, which are Ayuka and NCRA. And then when you come in the lower region, Karnataka region, you have in the Bangalore, which is also known as the hub of astronomy. You have several institutes like ISC Bangalore, IEA Bangalore, RRI Bangalore. Recently, but there is ICTS also, which is more towards the gravitational waves studies. And then in the topmost northern region, you have Uttarakhand region, you have Aries in Nainital, which is in the hill region. So this is mostly of observational astronomy if you want to contribute in observational sciences. So apart from these, you have there are various other institute like institutes which have PhD programs, out of which are mostly ISRs, and you have IITs also. So like Mohali, Bhopal, and then you have Bombay and Pune and Trivandrum And then you have in Bangalore ICTS, which I already mentioned. Then you have ISRO, and then NISR in Bhubaneswar, and ISR. So SN Bose Institute, which is in Calcutta, and you have ISR Kolkata, and then you have Banaras University and HRI Allahabad. So these are the places where you can have pursue your PhDs in astrophysics. And I think there are many other IITs also which has uh, which uh, which provides PhDs in uh, uh, astrophysics, depending upon they have faculties in there. Like I remember IIT Kanpur, IIT Kharagpur, IIT Madras, they have there are also availability of doing pursuing theoretical astrophysics. So that was in the India. So suppose if you want to pursue your career in astrophysics in abroad, then there are two pathways. If you want to pursue in Europe, then you need to have a bachelor's in your physics, and then you have to have to give a English proficiency test, which is IELTS. That is for you can pursue master in Europe, and then uh, you can pursue PhD with these English proficiency tests. And if you want to pursue in USA, then you need to have a bachelor's in science, and then you need to give GRE as well as TOEFL. And based on your score, you will get the universities, and you can pursue with your masters. And similarly for PhD also, you need to give same exams, and you can pursue PhDs in astronomy. So as far as for scholarship in India, you receive around 32 to 35 thousand per month, and for abroad it may vary between 1,000 to 2,000 USD. So so currently it is like still you complete your schools, and before that how you can take up, how you can be updated with the research which is going on in the astronomy. So there are various other methods. You can be still, while you're in your schools, you can still be involved with the astronomy. Like you can attend the summer and winter schools which are conducted by various institutes, research institutes like IA, IUCA. They organize these schools, and you can apply to these schools, and you can interact with various faculties and students, and you will get many more insights in the astronomy. And then you can apply for internships, which can be from 3 to 6 months, and in these institutes like IAA, IUCA, PRLs, IITs, ISRs. And then you can apply to bachelor's and master projects if you are doing BSc in your any of the Indian university. So you can still apply for this projects which you are supposed to do in the last year of your bachelor's or master's. And these many of these institutes organize science day activities, which is around February. And so you can you can have the opportunity to talk to students and faculties. And if you are not sure that you want to pursue a career in astronomy, but if you want to pursue it as a hobby, then also you have plenty of opportunity throughout, because you have a lot of planetarium around where they organize skywatch session. And there are around 47 permanent planetarium in India, and they have public astronomy and space wing programs. So you can take advantage of this and pursue your fascination or as a hobby. And you can join the astronomy clubs and interact with the amateur astronomers. Like you have these many like in Bangalore and Ahmedabad, as well as Pune and Delhi. You have these centers where and societies where you can interact with the people which are involved with amateur astronomy. And you can also take part in national and international astronomy olympiads. And then you can also contribute to, like, there are many projects which allow public to share their opinion about any objects, astronomical objects. Like in Juniverse, there is one program that you have to you have to tell by viewing the galaxy, you have to tell which shape it is. So in that way, because in universe you have millions and millions of objects, and they want to engage people to help them such that they can they can resolve the data very easily so you can be part of these projects. And in Bangalore there are REAP courses which are going on for uh, so which provides like 1,000-hour certificate course, so you can go and you can attend these programs and take benefit, and where you will know a lot of fundamentals of astrophysics. So, and yeah, I think with this I will end, and if you have any questions you can type in the form which is provided you in the link below. So now we will move to question and answer session. So in the carrier there is a question which is, can I make the question is by Rohan Garate, can I make career in astrophysics by studying in IISc? So this will be answered by Ramya.
Yeah, hi. Actually, Sandeep himself has one of the student of IISc. He just finished his PhD. So IISc Physics Department offers a course called as Joint Astronomy Program. So you can join there after your engineering or your Masters in Science, and you have to pass one of the qualifying exams. So once you are done with that, you can do a physics. You can do a PhD in astronomy in IISc.
Yeah,
Thank
thanks,
you.
Ramya. So the next question is, what are the career options for biology background student by Vanchika? And that will be answered by Arun.
Thank you, Sandeep. That's quite a good question because one of the up and coming areas, hot topic is astrobiology, which looks at the possibilities of existence of life on planets outside our own and even outside our own solar system. So astrobiology is a very promising opportunity. Unfortunately, as of now, there are no institutions or universities in India which offers course in astrobiology as such. Of course, there are universities abroad, especially US and Europe, which offer courses, both undergraduate and higher courses in astrobiology. But in India, in the meantime, there are certain outreach programs, and there are certificate courses that are offered in astrobiology. For example, Bangalore has Birla Institute of Fundamental Research, which offers a short-term course in astrobiology, and there are also newsletters and various public forum available for understanding various aspects of astrobiology. Thank you.
Thanks, Arun. So we will now move to general question and answer session, and where we will answer all the questions relating to day night as well as night time, and some carrier questions also. So the question in daytime astronomy, which was asked by Parak Agarwal, what will happen to Earth without magnetic field in the Earth? So this will be answered by Avijit. Avijit.
Yeah, thanks, Mark. That's a very interesting question. So we saw that it is whenever we have this explosion of plasma as a result of the reconnection of the magnetic fields in the sun, we have a huge emission of plasma blob that is launched towards the Earth. And it is the Earth's magnetic field that kind of shields us from this incoming ions. And it is because these charged particles follow the Earth's magnetic field that they reach our poles and they appear as auroras. So if we don't have the shielding that we get from Earth's magnetic field, then we will have a bombarding of this hugely highly charged energetic particle that will hit us, and that would be that can short circuit our power grids, it can disrupt our transportations, and it can even have harmful effects on us. So we should be kind of grateful that we have the shielding because of the Earth's magnetic field. Yeah, thanks. A good question.
Thanks a lot, Avijit. So the next question is slide number 13 in this daytime astronomy. Why is the temperature in chromosphere increasing? This question is by Sai Siddhartha, and this will be answered by Supriya. Supriya.
Yeah. Hi. A very interesting question. In fact, chromospheric and coronal heating is one of the open problems in the field of solar physics. Basically, like you understood from the talk, is now once we are further moving away from the photosphere to the upper atmospheric regions of the sun, we start seeing the increase in the temperature. There are many theories that are proposed to explain why this happens. One of the theories is to explain it through the magnetic field activity. So basically, the magnetic fields that are originating from the photosphere gets further stretched to the higher atmospheric regions. So when you're moving up like this, like imagine you're stretching a rubber band further. So at some point, you keep stretching the rubber band and it breaks, right? Releasing the energy. It's something similar. These magnetic fields, after some point, they break, releasing the energy. So this energy heats up different layers of the atmosphere. Or it can also be because of the crossing of two open magnetic fields that are originating from the lower layers. So this is one of the theories through which scientists try to explain why there is heating of the upper layers after the photosphere of the sun. Thanks.
Thanks a lot, Supriya. So the next question is a very interesting question. So this question is by Vanshika. So the question is, in the initial stages of universe, if matter was so compact, how did the universe not collapse in a black hole there itself? So this will be answered by Swagat. Swagat.
Hi, this is a very interesting question. This is a question that even I had when I was a student. Uh, so imagine universe expanding. So we know as universe is expanding, there are all these galaxies or matter, and they're going away from each other, but they're trying to pull themselves due to gravity. So the question is, if they were very closely spaced early times in a compact way, then why wouldn't they collapse to form a black hole? Well, we can understand this by looking at how we can throw a stone from Earth. Okay, so think of Earth's surface and think of throwing a stone. If you throw the stone with a speed smaller than about 11 kilometers per second, then the stone is not going to leave Earth. So it's going to go up and up and up for a while and stop there and fall back, which is what we usually see. So this could have happened to the universe. Or the other possibility is, if you throw it with a very high speed, greater than the escape speed, then it will just go away and never come back. So it will go from Earth, slow down, but it will never come back. It will never stop. So it depends on what is this initial speed that you give to the stone. The same thing also depends in the universe. What was the initial velocity with which universe started expanding? So if you go to an early times, it turns out the initial velocity with which universe was expanding is sort of very, very close to the escape speed. Had it been smaller than escape speed, it would have turned back. So even though it was dense, there was enough expansion speed not to reverse the direction of expansion and collapse it. So it kept expanding for 13.8 billion years, and it seems like it's going to expand for quite some time. In fact, if we understand if you understand particularly dark energy as cosmological constant, then it's going to expand forever. It's not going to come back.
Thanks, Swagat. So the next question is, so it's a very interesting question. It's relating to the Interstellar movie. So in Interstellar movie, does 5D really exist? And what is exactly 5D, which is, I assume, 5 dimension you are talking about? Does it really take you to the past or future? So this question is by Sahana Bhatt and it will be answered by Prashant. So Prashant, over to you.
Hi, Sahana. It's a very nice question. And it's also interesting because we watch movies, and movies these days are dealing with complex phenomena in physics also. That's nice. So interstellar introduces the popular concept of how higher dimensions can be visualized, 5D in this case. If you can think of our visual space, we live in a 3D space, and time goes along. So we have 4 dimensions. Imagine ants moving along the ground. Do you wonder if the world is 2-dimensional, or do they ever look up? So we could be like these ants in our own 3D world. If you could trace each and every moment of your life, you may visualize each as a snapshot in time. So if you have an additional space dimension, you may be able to look from above onto each of these snapshots. So the movie takes liberty in allowing the main character to interact with some of these snapshots in their life. So there is a lot of creative liberty taken in the movie. But yeah, it's just very interesting to think of what it might mean. Thanks.
Thanks a lot, Prashant. So the next question is also very interesting. It's related to cosmology. So it is, what is our universe is expanding into? So it is by Sachetas and will be answered by Akansha.
Hi. Yeah, so when we say what is the universe expanding into, this is intuitive to us because when we talk of expansion, we think of some container and maybe something is expanding into it. But we have to understand what really expanding universe means. So here the universe is not really expanding into something because there is nothing other than the universe here. This is the property of the space inside the universe. So you can imagine that instead of something expanding into a container, it is like something like more space is being created. You know, when you stretch a rubber band, what you really feel there is that there is more rubber band being created when it's actually so this is how you can visualize it. So it's expand because universe, we don't have any boundary or anything or any outside thing or some container into which it is expanding. So it's not very intuitive to us because our understanding of expansion is always inside something. So this is not how expansion is. I hope I made it because it's very difficult to imagine this concept. So yeah, thanks.
Yeah, thanks a lot, Akansha. So next question is about carriers. So which is asked by Rohan. And the question is, do NASA have recruitment for astrophysicists? This will be answered by Sayali. Sayali, over to you.
Yeah, hi Rohan. Yeah, so the short answer to your question is yes. The longer answer is that you have to go through a process, such as you have to work on research and during a master's and PhD. And they do offer postdoctoral opportunities. They have something called a program called NPP. So you can work really hard on your research, publish papers, and then write proposals to get the NASA fellowships. And yeah, that's how you can get into NASA. You have to work on your PhD first for that. So.
Thanks, Sayali. So the next question is by Siddhant, which is, how do we find the temperature of the core of the sun? That's very interesting. So this will be answered by Avijit.
Yeah, that's a very interesting question. So basically what we look at is that how the sun is in sort of an equilibrium between the hydrostatic pressure. So the hydrostatic equilibrium is something like the gas pressure that is sort of trying to contract, and then you have the gravity that is pulling it and the gas pressure that is expanding. So what we do is we take an equilibrium between this gas pressure and the gravity, and we try to find out, okay, at what temperature will the expansion or the gas pressure will balance the gravity. And when we look at that, when we find that a temperature around few million Kelvin is where we get this equilibrium. At the same time, we also see that, okay, at what temperatures the fusion reactions can happen. So we know that, okay, you have this hydrogen atoms which are fusing into helium. So there's a critical temperature only above which we can have this. So given these two conditions, we can get some estimates about what is the core temperature of the sun. Thanks.
So then, thanks, Avijit. So the next question is about sun only. So this is more general question by Satish Kumar, which is how the stars are formed and why the sun is only hot. So Shubham will be answering these questions. Shubham, over to you.
Yeah, thanks. So as Ajay showed in his talk, the stars are formed from molecular clouds. So when a clump in this cloud starts contracting due to its self-gravity, and eventually the core of this cloud becomes hot enough that the temperatures are high enough that hydrogen burning can start. And once that happens, the star enters its protostellar phase and then eventually joins the main sequence as a newly formed star. So as far as the sun, if I understanding it right, I think the question is why is it that only the sun is hot and not the other stars? And the answer to that would be, well, the stars are also hot. It's not just that the sun is hot, but the sun is much closer to us, and that's why it appears so much brighter in the sky. The stars also have temperatures, and in fact, the color of stars is a good indication of their temperature. So the bluer the star looks, the hotter it is, and the redder ones are the cool ones. Thanks.
Thanks, Shubham. So the next question is by Siddhant only. So this question is how close we can send and satellite to sun. So this will be answered by Krishna. Krishna, over to you.
Hi, Siddhant. So it's a nice question. So currently, there is one satellite on its approach to the sun. It is Parker Solar Probe. So it has been launched a couple of years ago by NASA, and it is expected to reach as close as 7 million kilometers from the surface of the sun in the next 5 years. So to put it into perspective, like that is the distance between sun and earth is 150 million kilometers. So it is about like 100 or 15 times less than 1/15 times less. And another way of thinking it is the distance between Mercury and sun is about 50 million kilometers. So you can imagine like how close this satellite is going to get. So the previous, so is it the closest we can reach? Perhaps, likely not. The previous closest was in 1970s. So Helios spacecraft, which reached about as close as Mercury is, like about 50 million kilometers. So in the last 30 years, like we have another probe, which is reaching almost 7 times furthest. So maybe in the next 15, 20 years, we might reach even further. Yeah. Thanks.
Thanks a lot, Krishna. So next question is very interesting regarding the carrier in the astronomy. So yeah, so the question is by Shikhar, which is how much knowledge of math is needed for carrier in astronomy? So this will be answered by Akansha. Akansha, over to you.
Hi, Shikhar. So since at school level, if you want to enter into astronomy later on, you would require knowledge of physics, because as you would have seen in the talks, it's all physical processes that we talk about, right from not just fundamental physics, even some amount of engineering. And both physics and engineering requires you to have good hold over mathematics. While if you are thinking of something on the amateur level, then you do not require. But if you need something on a professional level, at a career level, then yes, you require a good know-how of mathematics.
Yeah, thanks, Akansha. So the next question is by Rohan. So it's very interesting question. It is there any formula till now to measure the band in fabrical space-time? This will be answered by Prashant. Prashant, over to you.
Yeah, hi Rohan. Yes, the short answer is yes, there is a formula. But first of all, let's see what space-time is. it can be thought of as coordinates describing an event. So event could be something like a gamma ray burst or a supernova or something going on in the sun, which you measure at one point in space and time. So general relativity of Einstein describes the way how relative space-time coordinates are affected by and can affect the motion of massive objects. So anything which occupies space and time affects space-time, and space-time curvature affects that. So in general, space-time is a region around this massive object, and it may not be straight lines like what you would see in geometry as straight lines, but it could generally be curved shape. So this curved shape or bending of space-time is governed by a quantity called curvature in general relativity. Now coming to your question, is there an equation that describes the bending of space-time? Yes, so this is the Einstein field equation, which relates how curvature is related to energy content in the massive object. The equation can in principle be solved to find out how the curvature of space-time is affected by the presence of this massive object. Also, it gives you a visual picture of how curvature of space-time affects the motion of the massive object. So what you consider as a force which acts between two massive bodies governs how things move around each other. Thanks. So the
Thanks, Prashant.
equation is the Einstein field equation.
Okay, yeah, thanks, Prashant. So the next question is by Shikhar, which is, why can't a 30-meter telescope be built in space or in a space station? It's a very interesting question, and it will be answered by Siddharth. Siddharth, over to you.
Okay, so sorry for the background echo. To answer that question, the reason is the following. So we are just about able to make 30-meter class telescope on ground, and it's turning out to be a big challenge. And it's basically combines all the state-of-the-art technology right now to make 30-meter telescope on ground. And the overall mass of the weight of the whole telescope would be easily some 10-20 tons or more. So then, as you can imagine, the problem to make a 30-meter telescope in space becomes, how do you send that much mass, weight, instrument, an instrument to space? So once a rocket, you don't have that big a rocket capacity to send that much mass in space. Also, with 30-meter telescope right now, we're just about, we're understanding how to make 30-meter telescope. So once we get the understanding, then we want to send it to space. So usually the way it works is you try something out in ground-based instruments. You make a big telescope on ground and see how it works, whether you're successful or not. And then some years later, when the rocket capacity, the capacity of your rockets becomes big enough to send that big an instrument, you send it to space. So that's usually the chronology. You first do it in ground, where you can change anything that you need, and then as with time you with bigger rockets send that to space. So the quick answer then is that sometime in future, not now, because mainly of the rocket capacity as well as understanding how to make 30-meter clusters.
Yeah, thanks, Siddharth. So the next question is by Rohan, which is there any correct formula for theoretical explanation of dark matter given yet? So this will be answered by Bidisha. Bidisha, over to you.
Hi, Rohan. It's a nice question in the sense, like the name itself, dark matter, we call it dark because we cannot see it. So, but how do we know about it? I mean, as Akansha already explained in her slide, that the first evidence of dark matter came from galaxy rotation curves. I can share the slide maybe. Let me just, yeah, so can I share the slide?
Yeah, no.
Okay. Yeah. So as you can see that when the galaxy rotation curve is basically a plot of velocity versus radius for a galaxy. And so in general, whatever matter you see, the graph should follow this white curve. But when you actually take observations for farther and farther radii, you see that the velocity curve basically is more flat. And so this can happen only if there is more matter. So this is one evidence that tells us that there is more matter than what we see. But there is no exact answer for what this matter basically is. There are other evidences even from cosmology, like from CMB anisotropies. You have evidence that there is a lot of matter than what we actually see. By matter, what I mean is that they exert a gravitational pull, but there is no other interaction like other kind of matter, like which you can see, which interacts with light, and that's why you can see them. But this dark matter is something which you cannot see, and it doesn't interact with the known particles that are we know in the standard what we call as the standard model of physics. So yes, there are searches, like there are people studying supersymmetry models and other dark, but nobody is for sure yet. And one of the experiments, like the Large Hadron Collider, it tries looking for such particles, but till now nobody is sure of what dark matter actually is, other than the gravity part. Yeah, that's how I would like to address it.
Yeah, thanks, Vidisha. So we have many more interesting questions, but we are also limited by time. So I will take one final question, and after that we will conclude the session. And the final question is very interesting in this. So this is by Nakshatra, which is what happens to the Earth when sun explodes? This will be answered by Jay. Jay, over to you.
Thanks, Nakshatra, for this wonderful question. And so, as in one of the slides I had previously mentioned, so when the fusion reactions in the core of the sun would stop, its outer layers would start expanding, and it would become a red giant. And this would happen, and its size would increase 100 times. And in the process, when it becomes a red giant, it would engulf all the planets around, a couple of planets at least around it. So just like Mercury, and in fact also Earth. So before even exploding as a planetary nebula, the Earth would already be engulfed into this red giant that the sun would become. And I hope that answers your question.
Thank you, Jay. So I will, with this, we will like to conclude our session. And before that, I would also like to mention that for those, there are many questions which has not been answered yet. So please don't feel bad. Still, you can ask more questions to the email ID which we have provided. So which is askastronomer@gmail.com. So we will, and there are many more questions which are still asked but not answered. We will be putting these questions into our FAQ, which you can check on our website. And if you have further many other questions, you can still ask to our email ID. And so we would like to conclude with this, and please stay safe and enjoy your days. Okay.